Hi, welcome to Chapter 5, Section 4. At the top of the page, we're dealing with medians and altitudes. Don't forget to put the date at the top of the page. The first definition is for the median of a triangle. It's a segment with endpoints at the vertex of the triangle and at the midpoint of the opposite side. And the three medians are concurrent. So we want to also point out that the point of concurrency is called the centroid of the triangle, okay? So that's an important definition. And also up here, the median of a triangle is an important piece of information. We also should take note here, just because it'll make it easier to find when we're flipping through our notes, that median is from vertex to midpoint. Okay, that's an important part of that definition, that the median goes from the vertex to the midpoint. That's a funny looking R. Anyway, continuing on. At the bottom of the page, we have the concurrency of medians theorem. It says the medians of a triangle are concurrent at a point, this is K here, at a point which is 2/3 of the distance from each vertex to the midpoint of the opposite side. Now we should also make note up here at the top that in this picture, point K is the centroid of triangle ABC. Okay, so what that's, using the theorem, what it's saying about the picture is AK, this segment from the vertex to the centroid, is 2/3 of the entire median. And it says the same thing for the median BF and for the median segment CE. Now, you also can take that information a step further, because if AK is 2/3, you can also say that KG must be 1/3. You can say the same thing about KF being 1/3 of the median segment BF. And you can say the same thing about KE being 1/3 of the median segment CE. Now, if you have a 2/3, 1/3 relationship, that also means that AK must be double KG. That means that BK must be double KF, and that means that CK must be double KE. There's a lot going on with this stuff. Now, there's a fourth, or actually 4th relationship that you can talk about, because again, if KG is 1/3 of the entire median, that means, well, it's just an adjustment of this. I can say 3 kgs makes an AG. Multiply by 3. 3 KFs makes a BF. Multiply by 3. 3 KEs. If you'd like to, you can make note of that over here on the side, that 3 kgs equals an AG. 3 KFs makes a BF. And 3 KEs makes a CE. Okay, so there's a lot going on with these medians. Keep this in mind, and we're going to move on to page 2. Okay, on page 2, we have a new definition for the altitude of a triangle. And the altitude of a triangle is the perpendicular segment from vertex to a line containing the opposite side. Now, the reason we say it's a line containing the opposite side, because altitudes can actually end up outside of the triangle, okay? So here we have an acute triangle. And when you have an acute triangle, your altitudes meet and are all inside of the triangle. When you have an obtuse triangle, two of your altitudes will be outside the triangle. And when you have a right triangle, two of your altitudes are actually sides of the triangle. So I'm going to go ahead and I'm going to take the highlighter, and in the two pictures where the altitudes are outside the triangle, I'm just going to go ahead and make those two altitudes pink so that you can see the two altitudes. Now here we can obviously see altitude segment CK, but we also have these guys are also altitudes. The legs of your right triangle become the altitudes of the triangle. Okay, so we have a theorem at the bottom of the page, and it says the lines containing the altitudes of the triangle are concurrent. And if you continue on to page 3, we're going to see the picture of what happens when those three altitudes meet. Okay, the point of concurrency of the altitudes, we're on page 3, is called the orthocenter of the triangle. Okay, it's a cute little name. So orthocenters can be either inside, outside, or on the triangle. So in this first picture, this is an acute triangle, and your orthocenter is inside of the triangle. In the second picture, we have an obtuse triangle, TCU. You can see your altitudes, and you can see your orthocenter, where those three meet each other. Again, in this picture, I'm going to make the altitudes of this obtuse triangle, I'm going to make them pink. And then in this last picture, we have a right triangle, and I've extended out the altitude so you can see them coming out here, these dashed lines. Your orthocenter is the vertex of the right angle, and once again, I will make the altitudes of this right triangle pink so that you can see them. And you can also see that our orthocenter is there at the vertex of the right angle. Okay, those are our definitions. We're moving on to page 4, where we're going to see some examples. Okay, we're here on page 4. We're starting with the first examples. We have this triangle, and we're being told X is the centroid. We can also see that X is a point of concurrency for these three segments, and therefore these segments are all medians. So that's a midpoint, that's a midpoint, and this guy's a midpoint. And let's just say here where medians meet. Medians again, vertex to midpoint. Okay, so the first thing we're being told is that CW is 15, and we're being asked to find CX and XW. So the first thing I recommend is write down the relationship without using any numbers, just what seems logical. So we know from the concurrency of medians theorem that CX is 2/3 of CW. With that in mind, I can substitute in that CW is 15, that's 2/3, is 15, and then that creates an answer that CX must be 10. Now, for the second part of this problem, they're asking for XW. You have several options. XW is half of CX. I like that one myself. But you can also say XW is 1/3 of CW. The choice is yours. Either way you stack it, you should end up with an answer of 5. And I'm going to say that I use this. XW is half of CX to find it. For the second one, you're being told BX is 8, and you're being asked to find BY and XY. So let's do the easy one first. If BX is 8, XY is half of bx. And so we can say that xy will be half of 8, which of course is 4. Now, we're also looking for by, and the relationship there is that bx is 2/3 of by. So I know bx is 8, so I substitute that in. And now I'm going to have to do some algebra. I'm going to multiply by 3. And I'm going to divide by 2. And by turns out to be 12. For the third one, why don't you go ahead, stop the video, and try the third one. Okay, for the third one, I went ahead and said if you triple xz, you get az. I substituted in, so az turned out to be 9. And then I said if you double xz, you get ax. So I substituted in and got ax was 6. Hopefully you got the same thing. Okay, for the second or fourth question, it's asking you to decide if segment AB is a median, altitude, median, or neither. How about that? We duplicated median. So let's get rid of that. Okay, so in the picture, segment AB is starting at a vertex. And based upon the markings, we can see that it's going to a midpoint. So vertex to midpoint is going to be median. Okay. In this picture, we see segment AB is right here. We also see that it's making a right angle with the extension of this side of the triangle. Well, when you have a segment that starts at a vertex and is perpendicular to a line containing the opposite side, then you have an altitude. In this picture, vertex to a point, but this piece is 2 and this piece is 3, so this is not a midpoint, this is not a median, and this would be neither. Also, it's definitely not an altitude because we have no right angles happening here. For D, if you take a look, for D, vertex to point, we have a right angle. It's hitting the opposite side. That's going to be an altitude. Okay, in the bottom picture, you're being asked to name the centroid. So centroid, you can see here, we're going from vertex to midpoint, and I need to have that 2/3, 1/3 relationship. That means I need to break this up here, and U is our centroid. And in the other picture, I need the orthocenter. So I take a look here. My 3 altitudes are CE, FB, and AH. And those guys are meeting right here at point X. And that is it for 5-4. You're going to want to watch the constructions for orthocenters and centroids.